Have you ever stopped to wonder why so many people fear uranium, yet so many countries go to great lengths to get their hands on it? While most see just a dangerous metal, others view one of the most powerful energy sources humanity has ever discovered. And the strangest part is that it comes out of the ground in the most ordinary way, hidden inside rocks like just another mineral. But turning that raw material into nuclear fuel is not as simple as pressing a button. It's a long, expensive, and delicate process. It involves deep mines, chemical reactions, isotope centrifuges, and millimeter-level precision. All of that to make something so powerful it can power thousands of homes for months with a single capsule, or in the wrong hands, change the course of a war. What few people know is what really happens behind the scenes, how this material is extracted, purified, and shaped with such strict control, and why it remains wrapped in rules, political tension, and international disputes. If you're like me and you often ask, "How is this made?" or "Who had this crazy idea first?" then you're in the right place. Nobody wakes up one morning and simply decides to make enriched uranium. Before it becomes the fuel that runs entire nuclear reactors, uranium has to go on a long, underground, precise journey. It all starts with mining the ore, and this isn't done with ordinary shovels or backhoes. Uranium is taken from deep mines, often in unstable ground, where the rock must be frozen with brine at 30 degrees below zero to prevent collapses and water ingress. This freezing done through pipes installed around the deposit lets workers operate more safely, even without touching the material directly. After it's removed, the raw ore goes through an initial sorting. Larger chunks are broken with hydraulic hammers and then sent for intense grinding. The rock becomes a powder as fine as beach sand, but it's still not pure uranium. That powder is mixed with water until it becomes a thick mud, known as slurry, which is hauled by trucks to specialized plants. There, one of the most critical steps begins: the acid bath. The acid dissolves only the uranium and leaves other minerals to settle at the bottom of the tanks. It's a chemical cleaning where only what matters survives. But the uranium that comes out of that step still can't generate energy. It needs to be turned into a gas, centrifuged, and separated into different isotopes. This is where uranium-235 becomes the real star of the show. The gas is placed into centrifuges that spin at extremely high speeds to separate the lighter uranium-235 from the heavier uranium-238. The process requires microscopic precision, since the mass difference between the two isotopes is tiny. After separation, the enriched uranium is converted back into a powder, pressed into small pellets, and finally loaded into zirconium metal tubes, ready to become fuel. And up to this point, all of that has been just the beginning. What we call uranium doesn't come ready to use. It's disguised inside a dark, heavy rock that many people ignore because they don't know what to look for. That rock is called uraninite, and inside it hides uranium oxide, which makes up only a small fraction of the total mass extracted. The largest reserves are located in places like Canada, Kazakhstan, Australia, and Namibia, regions that, by coincidence or not, hold a good part of modern energy power. For each ton of rock pulled out of the ground, less than 1 kilogram of usable material will be turned into fuel. Uranium is a natural chemical element, and what's most fascinating is that it can be found in small amounts even in seawater and ordinary soil. But to be economically viable, it needs to exist in high concentrations, which only happens in specific deposits. Some of these deposits were formed billions of years ago, when the Earth's crust was still young. Deep underground, pressure, heat, and time did their work, until layers of rock rich in radioactive minerals were pushed closer to the surface by geological movements. Today, mining those rocks is like digging into the deep past of our planet in search of the fuel of the future. The color of the ore also tells a story. It ranges from brown to shiny black and is often mistaken for coal or basalt. But those who know what they're looking for can tell the difference. The density of the material is striking, and a simple Geiger counter can confirm it. Inside that rock, radiation pulses quietly. The raw material of uranium is both simple and powerful. A rock the size of an orange can hold more energy than entire barrels of oil. That's what makes uranium such a highly contested resource. And as the world searches for clean and steady energy sources, the race for this mineral keeps growing. Uranium enrichment is one of the most delicate and ingenious steps in the entire nuclear chain. To give you an idea, the difference between natural uranium and the uranium used as fuel lies in less than 1% of its composition. Uranium-235, the isotope that really matters for generating energy, represents only a tiny fraction of the total. Separating it from uranium-238, which is much more common, requires centrifuges that spin so fast they can exceed 100,000 revolutions per minute. It's like trying to separate two types of flour that look identical, using only only the difference in the weight of each grain. Now here's one of the most impressive parts. A single compact uranium capsule, about the size of a thick coin, holds enough energy to power a home for years. Just to compare, it can produce as much energy as 800 kilograms of coal or 560 liters of oil. And the most curious part is that this energy is released without burning anything. There's no smoke, no flame, just atoms quietly splitting and releasing heat. That's why, despite the ongoing debates about safety, nuclear energy remains one of the most powerful sources on the planet. These capsules are placed inside tubes made of a metal called zirconium, which is extremely resistant to heat and corrosion. But zirconium's real trick lies elsewhere. It allows neutrons to pass through. That's essential for keeping the chain reaction inside the reactor running continuously. The assembly of these tubes is done by automated systems in controlled environments where even the air is filtered. A misalignment or a tiny welding flaw can render an entire batch useless. All of this shows how precise the engineering behind enriched uranium truly is, down to the smallest detail. The name uranium was given in honor of the planet Uranus, shortly after its discovery in 1789 by a German chemist named Martin Heinrich Klaproth. At the time, no one could have imagined the massive impact this element would have on the modern world. It was seen as just another dark, dense metal, difficult to work with and without any immediate practical use. It wasn't until the 20th century that science began to uncover its true potential, when researchers discovered that its atoms could be split, releasing an enormous amount of energy. And that discovery opened the door to a new era in human history. The most fascinating part is that uranium is not our invention. It has always been there. More than 1 billion years ago, deep beneath Africa, natural nuclear reactions happened spontaneously. One of the best-known sites is Oklo in Gabon, where the ground itself acted like a natural reactor for thousands of years. No human intervention, no control, no engineering. Nature alone showed that nuclear fission could occur, as if giving us a sign that this energy was part of the planet long before we arrived. A natural experiment that still puzzles scientists today. For a long time, uranium was used in very different ways, far from energy production. In the 19th century, it appeared in glass and ceramic coloring. Some objects from that era still glow green under ultraviolet light because of uranium in their makeup. Everything changed when the element began to be studied in military laboratories. In 1945, the world witnessed uranium used as a weapon in the first atomic bomb dropped on Hiroshima. From that moment on, uranium became a paradox, a source of clean, powerful energy, and also a symbol of destructive power when applied to other ends. Few materials have shaped modern civilization as much as uranium. In times of energy crisis and in the search for cleaner alternatives, it appears as a potent and steady source. Unlike solar or wind power, which depend on the weather, uranium can deliver stable production all year long. A single capsule can power hundreds of homes for months without emitting polluting gases into the atmosphere. For that reason, many countries see uranium as a bridge between the present and a more reliable energy future. But uranium's importance goes beyond numbers. It represents a shift in thinking. While the world debated coal, oil, and gas, scientists discovered it was possible to split atoms to produce heat. That leap from the visible to the invisible ushered in the atomic age. Uranium became a symbol of progress and also of responsibility. After all, the same process that drives turbines can, in another context, devastate entire cities. It is a force that demands maturity from those who control it. Today, uranium powers reactors that supply metropolises, hospitals, and even nuclear submarines. It keeps military ships running for months without refueling and provides isotopes used in radiotherapy to help treat many kinds of cancer. Its uses go far beyond electricity generation. In each gram, there is an almost invisible potential for transformation, for better or worse. Maybe that is why uranium remains one of the most studied, monitored, and protected elements in the world. The story of enriched uranium production begins in the heat of World War II. It was during that time that the United States launched the Manhattan Project, a secret effort to develop nuclear weapons. Back then, the technology to separate uranium isotopes was still in its infancy. Large calutrons were used, enormous circular magnets that consumed huge amounts of power and produced only tiny amounts of useful material. Everything was slow, experimental, and costly. Even so, that first step changed forever how humanity deals with atomic energy. After the war, the race shifted from military to energy goals. Research turned to more efficient enrichment methods, and centrifuges began to take center stage. Unlike the old techniques, centrifuges separate isotopes using only the small difference in mass between particles, without relying on giant magnetic fields. This made production cleaner, safer, and more compact. Countries like Russia, Germany, and Japan invested heavily in research and engineering to refine their own enrichment systems. Today, the process is almost surgical. Modern centrifuges operate in cascade, with hundreds working in sync inside highly controlled environments. Everything happens quietly, with sensors watching temperature, vibration, and density in real time. If in the past an entire room was needed to produce a few grams of uranium-235, today a single production line can supply a reactor for years. The technology has evolved, but the principle remains the same: extract, separate, and transform a raw material into one of the most powerful fuels ever known. After all the chemical, physical, and industrial processing, enriched uranium finally takes its final form: dark, dense capsules precisely placed inside metal tubes. These tubes, known as fuel rods, are grouped into larger assemblies ready to power reactors. Each assembly is carefully inspected, weighed, and sealed. Nothing is left to chance. The margin of error here is practically zero. Before being shipped, everything undergoes integrity tests that simulate vibration, temperature changes, and even impacts. Safety is treated as an absolute priority. Transporting this material requires strict protocols. The fuel assemblies are placed inside shielded containers made of reinforced steel, designed to withstand severe accidents. Special trucks, equipped with escorts and monitoring systems, follow routes approved by authorities. In some cases, transportation is done by rail or sea, depending on the destination. The distances can be vast, since not every country that uses nuclear energy has its own enrichment facilities. This makes logistics an international scale challenge. At their final destination, the fuel assemblies arrive at nuclear power plants, where they are precisely inserted into the reactor core. Before that, they go through radiation and stability inspections. Only when everything is approved is the material cleared for use. From that point on, what once was just a rough rock buried under tons of earth begins generating electricity for entire cities. It's an invisible process for anyone who simply turns on a light at home. But it starts long before that and involves one of the most sophisticated industrial chains in the world. It's hard to imagine that all of this starts with a stone buried in the middle of nowhere. What once seemed like just another mineral becomes capsules capable of powering entire cities. Machines operating in silence, sensors that never sleep, tubes welded with microscopic precision to contain something we can't even see with the naked eye. All of it working to turn invisible matter into energy. But as we admire the precision of centrifuges and the perfection of assembly lines, one question remains impossible to ignore. Behind all this technology, where are the people? Who envisioned all of this? Who first had the idea to split an atom? Humanity is capable of creating processes this sophisticated, but also capable of using that same energy to destroy. And when the line between progress and power blurs, the greatest conflicts in history are born. If you've made it this far, leave a greeting in the comments and tell me which city and country you're watching from. And of course, like this video and subscribe to the channel so you don't miss what's coming next.